pages or something. Nobody wants to sit.
Yeah, I probably am. We probably all are. So I'm going to do, or at least talk a little bit about numbers 2 and 5. 2 is kind of an important conceptual one. So, okay, based on the matrix relationships between stress and strain, it asks for what stress values does the X normal strain depend on? So all of these questions are kind of asking like, well, what if you didn't know the whole Voigt stress, but all you wanted was the X Voigt strain, normal strain? What's the minimum number of values that you need in order to calculate that? That's sort of what this is getting at. So this is strain and constitutive relationship number 2. And for A, you can think of it as like what's the least you have to know about the stress to calculate the X normal strain. Okay. And so all this is just based on these matrix relationships. So here's the full matrix relationship. I literally still, when I'm writing Voigt stress or Voigt strain and I get to the shears, I still literally think like, this is the order that would make sense, and then I reverse them. Like, that's how I think of it. So then we have our compliance matrix, 1 over E, negative nu over E, negative nu over E, 0, 0, 0. Negative nu over E, 1 over E, negative nu over E, 0, 0, 0. Negative nu over E, negative nu over E, 1 over E, 0, 0, 0. And then 0, 0, 0. 2 times the quantity 1 plus nu over E. And then that just moves along the path. And this is multiplied by stress XX, YY, ZZ, and then the shears, YZ, XZ, XY. Okay. So now we're gonna, in order to figure out the dependence, like the stress dependence that you have to calculate EXX, let's just do that matrix multiplication. So remember that the way this works is we're going to take a dot product of this and this, okay, to calculate that EXX. And so EXX is equal to 1 over E times sigma XX minus nu over E times sigma yy minus nu over E times sigma zz, and then plus 0 times tau yz plus 0 times tau xz plus 0 times tau xy. And so this is the relationship that you have. Okay, so in other words, to calculate sigma xx, you need all the normal stresses but no shear stresses. Okay, so that XX normal strain depends on all of the normal stresses, but none of the shears. And then, I mean, basically this question is just asking you to think through these relationships. So what about EYY? Let's just think through all these. So EYY is equal to negative nu over E times stress XX plus 1 over E times stress YY minus nu over E times stress ZZ. Again, the shears don't come into it. But the key thing is, you might think like, oh, well, if I want to calculate the strain YY, the normal strain YY, maybe all I need is the normal stress YY. Well, that's not true. You need all three of those. Okay. Same thing with Z. I'll just write that here. So EZZ is equal to negative nu over E times stress XX minus nu over E times stress YY plus 1 over E times stress ZZ. Okay, so the take-home message for normal strains is to calculate any single normal strain you need all three normal stresses. By the way, it works in reverse too. If you have strain information and you want to calculate stress information, to calculate any single normal stress, you need all three normal strains, but no shears. Okay. So it's the same for calculating a normal stress from strain values. Okay, so, well, now let's think about the shears. Okay, well, now you might think, okay, well, if to calculate a single normal strain, you need all three normal stresses. It would probably make sense that to calculate a single shear strain, you'd need all three shear stresses. But that's not what happens if you multiply out the matrix, so let's look at that. So first of all, if you're trying to calculate gamma YZ, That's the fourth line here. So you get that by taking the dot product of this and this. And there's only one non-zero element in that, that first vector from the dot product. So what you get is that the YZ shear strain is equal to 2 times the quantity 1 plus nu over E times the corresponding shear stress. Okay, and that keeps going. So the take-home message for the shears is to calculate a single shear strain you only need the corresponding shear stress. And that works the same if you're calculating a shear stress from the strains.
Isn't the inverse matrix or the transpose matrix?
It's the inverse. Yep. And I believe on all PI calculators, you can do an inverse by just put in the variable that represents the matrix you want to invert, and then just raise it to the exponent -1, and it'll do that inverse for you. Okay, so the reason that I want you to think about this a little bit is because there'll be times where you don't have all the information available to you. You're given a hodgepodge of information, and somebody will want some small number of strains or some small number of stresses. Just remember, so you can't plug it into the full matrix in that case, but look and see whether you have enough information to calculate it. Okay? Sometimes you do. Are you with me on that? Okay. Any other questions about that problem? Okay, so now number 5. This is one where maybe I just made a mistake in the solution, right?
Yeah, I think so.
Okay. Okay, so we got,
Oh, yeah.
you got something different from me too?
Yeah, I kind of just figured it was like, I don't know, someone entered something.
I think it was a sign
Yeah.
error because I
Oh.
was able to get your answers by messing with.
Oh, okay. Yeah, that's very suspicious. Okay, so, all right, so first let's put this in a stress tensor.
But like when I did the sign switching, it didn't make sense with the formula.
Yeah, right, I got you.
I was like,
Okay, so, yeah. Yeah.
Does it matter if you're multiplying
Yeah.
different unit of Pascal?
Yes, it does. It makes a huge difference.
Because
because that compliance matrix has units. So your compliance matrix units have to match your,
I noticed that you use Pascals in the form matrix, but not in the other, like, has like the megapascals.
okay. Yeah, be very careful about that. It's an easy mistake to make. I was just trying to demonstrate how easy it is to make that mistake. Okay, so we got -5, +10, 0. Okay, so this is number 5. -5, +10, 0. That means this is 10. And we got nothing there. Nothing there. So everything else is zeros except a -20. So 0, 0, 0, 0, -20. And that means that the Voigt stress is -5, 0, -20, 0, 0, 10. And so I don't have a calculator right now. I think I let the battery run down too far on this one. I don't have one that has that programmed in for the compliance matrix, but so first I'll put it in pascals. And so the XX normal strain is equal to 1 over E times -5 times 10 to the 6 minus nu over E times -20 times 10 to the 6 EYY is negative nu over E times -5 times 10 to the 6 minus nu over E times -20 times 10 to the 6 EZZ is negative nu over E times -5 times 10 to the 6 plus 1 over E times -20 times 10 to the 6. And then 2 of these shear strains are 0 because they only depend on the corresponding shear stress. So the YZ strain and the XZ strain are both 0. And the XY strain is 2 times 1 plus nu over E times the XY shear stress. And 200 times 10 to the 9th for the Young's modulus is something you're going to see a lot. That's sort of a kind of an average value for steel. Different types of steel, different compositions, different amounts of carbon or whatever can change it a little bit, but that's about what it usually is. Yeah.
Is that engineering notation?
No, it's my notation. So yeah, I could have written it 2E11 I guess I wrote it, it's somewhere in between calling it gigapascals and calling it pascals, I guess is what that
you
is.
forgot a decimal and you just wanted significant numbers or something?
I think it's because I wrote it in pascals, but I was still thinking of it as gigapascals. And so I guess if you look these up, like you Google the Young's modulus for steel, it'll give it in gigapascals. So it'll tell you 200. So then I just wrote down 200, but then wrote it in pascals instead of gigapascals. I guess that's why. Anybody want me to go through those? I mean, I can calculate those constants, but it probably isn't super helpful.
Can you just calculate the first one?
Yeah.
Because I think you get like 5.5. And then your fact, I also forgot to do this, but I didn't convert the pascals or the megapascals.
Oh, yeah.
So your answers were also off by a factor of 5 or 6.
Yeah. Not by a factor of 5 or 6, by a factor of
like
100,000. So yeah, don't, when you're off a little bit on your exponents, that's a big problem.
Yeah, I didn't see that until she pointed it out.
Yeah.
I was like, wait a minute. I just have 5 pascals.
It's this damn wall fucking shtick.
So I got a value for EXX of positive 5 times 10 to the minus 6.
Yeah.
Okay. One thing about that's a little surprising if you look at what's going on, if you think about what these signs mean, because we have an XX normal stress that's negative, okay? So we're compressing, this thing is being, like, forces are pushing on it to compress it. How did we end up with it being stretched instead of compressed? Are you with me on what I'm asking? The answer is we're applying forces to smush it along the axis, but we're applying even bigger forces to smush it in the off axis. And remember that every time you smush, the other directions bulge out, okay? So the bulging out from this big transverse force here, this big transverse load here, overwhelms the smaller compression that we're applying that way, and we end up with a net effect of this thing expanding, even though we're trying to squeeze it. Yep.
So for it to have actually been compressed, it basically kind of have the L.
Yeah, right. Well, remember that, so look at the coefficients, you know, the one that's on axis, you're multiplying by 1 over E. The one that's off axis, you're multiplying by, say, 0.3 over E, you know. So this has an advantage in the math. But if that load is just a lot smaller than that one, it still can lose, yeah.
So it's like on their own, it's like there's your on their
Yeah.
access.
Right. Yeah, they get an advantage. They get home field advantage. You can still lose at home. Any other homework questions? So all this stuff is just like, there's a million new things. None of it is very hard to think about, but it's just a lot of stuff to get used to, you know. Okay. Well, let's go through a tensile test. And see how that would get used. So let's say that we have this unknown metal alloy, and we know that in the application, in the desired application, a point in the material, a point in the body made of this alloy has a stress of a stress tensor of 2 times 10 to the 7, negative 1 times 10 to the 7, 0, negative 1 times 10 to the 7, 0, 0, 0, 0, 8 times 10 to the 6. And this is in pascals. In order to figure out the deformation that's going to happen at that point, the strain at that point, we've prepared a sample of the material. This material I'm talking about, this alloy. In a tensile test. And so this tensile test looks like this. We've applied a total force this way and this way of 5,000 newtons. Before the deformation, the length this way is 0.1 meters. The length this way is 0.02 meters, 2 centimeters. And the thickness before the deformation is 1 centimeter. Okay. When loaded, we remeasure these lengths and we get the one that started as 0.1 centimeters now is 0.100, how many O's? 3 O's and then a 3. The one that started out as 1 centimeter. No, yes. The one why would I do that one? That's crazy. Oh well, that's what I got. So the thickness that was 1 centimeter is now 0.0049 and then a 2. And based on that, we want to know what's the strain of the point in that desired application. Okay, so we're going to use the tensile test to come up with a compliance matrix. Then we're going to use the compliance matrix with this known stress and calculate the corresponding strain. Okay? First, to calculate Young's modulus, remember Young's modulus is the XX stress, the loaded axis stress, divided by the loaded axis strain, normal strain. Sigma XX is equal to 5,000 newtons divided by the cross-sectional area. So the cross-sectional area is 0.01 times 0.02. These are meters.
Did I miss it, but did you define the coordinate system?
The coordinate system always is going to have the x-axis along the long axis. It could be either up or down, but let's use a coordinate system like x, y, and then z coming out. What? Oh, just because there's no reason you have to, but everybody has kind of agreed that they do it that way, so we're going to do it that way.
Okay.
Mathematically, there's no reason you would have to.
But that's how Young's modulus is defined, right?
See, the way I gave you the definition of Young's modulus uses this coordinate system.
Oh,
Last class, where you weren't here.
I watched the video.
Oh, okay. Okay, good job.
I missed like the whole beginning. There was
Yeah.
like, all right, now shut up. It's my turn. Like, look, you know. I was like, dang, I really missed like an entertaining lecture.
They're
All right. Thank you.
That's true.
If you love physics, they're all entertaining.
I like them for you.
Okay, well, notice that to calculate the cross-sectional area, you're using the undeformed lengths. Okay, it obviously wouldn't make hardly any difference at all. But when we're calculating those areas, you're using the before the loading happens. And so what we get for this is exactly 2.5 times 10 to the 7 pascals. And now we'll do the XX normal strain. Well, that is the deformed length. So 0.10003 minus the undeformed length divided by the undeformed length. And you get a value of 3.0 times 10 to the minus 4. A little bit outside of the range that I told you is kind of like a rule of thumb, but somewhere around there. And so now Young's modulus is 2.5 times 10 to the 7 divided by 3.0 times 10 to the minus 4. And you get a value of 83.6 0.3 repeating gigapascals, or 83.3 repeating times 10 to the 9 pascals. Any questions about anything I've done so far? And now we want to calculate Poisson's ratio. We are going to do that as negative y strain divided by the xx strain. We already have exx. Eyy is the deformed length in the y direction. So that was 0.0099992 minus 0.01 divided by 0.01. And you get negative 8.0 times 10 to the minus 5. So now the Poisson's ratio is negative of negative 8.0 times 10 to the minus 5 divided by 3.0 times 10 to the minus 4. And you get a Poisson's ratio of 0.26 repeating. Okay, so for the compliance matrix, 1 over E, wherever that shows up in the compliance matrix, you get a value of 1.2 times 10 to the minus 11th. The units are 1 over pascals here. Negative nu over E is negative 3.2 times 10 to the minus 12th, 1 over pascals. And wherever you see 2 times the quantity 1 plus nu over E, that comes out to be, oh wow, that got small. That comes out to be positive 3.05 times 10 to the minus 11, 1 over pascals.
This one is because the Pascal just needs low.
Is what?
That's why the strain value ends up being
Yeah, I mean, yeah, I think the easiest way to think of it is just from the definitions of the strain. You're just dividing lengths by lengths or radians by radians, but you can see how it's going to come out to unitless, yeah. And so this compliance matrix, I'm just going to put these values in, I guess, because then you can, if you want to fiddle with this and check your calculator and whatever you can. The compliance matrix is 1.2 times 10 to the minus 11, negative 3.2 times 10 to the minus 12, negative 3.2 times 10 to the minus 12, 0, 0, 0. Then minus 3.2 times 10 to the minus 12, 1.2 times 10 to the minus 11, negative 3.2 times 10 to the minus 12, 0, 0, 0. then minus 3.2 times 10 to the minus 12, minus 3.2 times 10 to the minus 12, 1.2 times 10 to the minus 11, 0, 0, 0. And then the thing that keeps moving along in the last three rows is 3.05 times 10 to the minus 11. So there's the compliance matrix. And now that you know the compliance matrix that represents that material, now we're not talking about, so like when I said in this desired application, a point in this body has this stress. Now we're not talking about this very carefully controlled little sample anymore. We're talking about any crazy shape made out of this material you want. And you know that at one point, the stress tensor is this thing that's given. How do you know what the strain is at that point? Multiply it by the compliance matrix. And so the Voigt strain is equal to that compliance matrix times the Voigt form of that stress in the application. So 2 times 10 to the 7, 0, 8 times 10 to the 6, 0, 0, negative 1 times 10 to the 7. That's what I gave you, right? Yes. And you come out with a strain of 0.000214, negative 0.00090, positive 0.00032, then 0, 0, and then the last element is negative 0.000304. So based on just that simple tensile test that we did, we can convert any stress that happens in that material into a known Voigt strain. Yes?
Can we just start with the stress tensor given?
Yeah.
I'm not remembering how.
We don't know how to do that yet, but we're going to spend, where did that stress tensor come from? We don't know yet, but we will spend half of this class or something just talking about, okay, now you have a beam with these loads on it. At this point, how do you calculate the stress there? That kind of thing. Okay, but right now we're just doing kind of like the setup. So, okay, we know like if someone gave us that stress, we could calculate the strain, but it's still sort of a mystery where that comes from. Any other questions? Okay, well, that's it for today. And then we'll, next class, talk about stress transformations, which is expressing a stress tensor in a new coordinate system. Yes?
Are there any materials that have just like a standard, like, compliance matrix?
A what?
Like, are there like materials that have a standard resolution stuff or like?
Not stress and strain values.
Like the compliance.
The compliance matrix, yeah, I mean, as long as somebody before has done a tensile test of that material, then you don't have to do it yourself. You can just look up the values.
But what if it's trending on like a certain batch?
Yeah, it can be. So, I mean, you need to be careful. Although, I should say too, with this stuff, this mechanics of materials stuff, you're largely just kind of looking for rough ballparks of these answers. You know, like when you do circuits, you're calculating stuff that's so precise and so accurate. This is not that level of accuracy. If you can get stuff within 10 or 20%, you're pretty happy.
Okay. Thank you.
Yeah.